We start with the classification of subgroups of Z plus. আচ্ছা এক মিনিট দাঁড়াও তো, প্রবলেম হচ্ছে। Okay, so let us start with the classification of subgroups of Z plus. That means we are to determine what are the subgroups of Z plus. Now, first of all, let us have a look at the following subsets. What are those? The subsets in Z. Okay, that means NZ means set of all integers which are multiples of n, right? So first of all we are looking at these subsets. Are these forming subgroups of the group Z plus? So let us check whether NZ forms a subgroup of Z plus. This is the question. Now let us recall that the criteria for a subset to be a subgroup of a group, we need to check that for n q1, n q2 be two elements of nz. Then we see that nq1 minus nq2 equals to nq1 minus q2. That means again this becomes a multiple of n. So that means it is in nz. So by the criteria that we have made for a subset to be a subgroup, that for any two element AB, you need to check whether AB inverse belongs to H. Now for additive groups, this is your AB inverse. This is your A, and minus NQ2 is B inverse, right? That is NQ2 minus of NQ2. The additive inverse of NQ2 is minus of NQ2. Okay, so that means with respect to this criteria, you can say that yes, NZ forms a subgroup of Z plus. Okay, for any n. greater than equal to 0. Okay. Now the question is that, does there exist any other subgroup apart from these subgroups in Z plus? Can you show any subgroup except these ones? So now your turn is to show that if we consider a subgroup, any subgroup H of Z plus, then our claim is that this H equals to some n naught Z or some n naught greater than equal to 0. Okay. So in view of this, you can easily conclude that yes, these are only the subgroups of Z plus for any n greater equal to 0. Okay. But how? So to show that this H is actually, so it takes the form n naught Z, and to show that this holds, you need to invite the well ordering principle of the non-negative integers, right? So suppose H is singleton 0, then we are done. We do not need to go further because it contains only the 0. So it is a subgroup and it is of the form 0z, because every integer is, which are multiples of 0, is 0. Okay. So let us suppose that H is not equal to singleton 0. That means, that is, there exists one A belongs to H which is non-zero, right? Right? Which is non-zero. Now, this A, maybe it is less than 0 or it is strictly greater than 0. Either A is strictly less than 0 or A is strictly greater than 0. Now, if A is strictly greater than 0, then we do not need to go further. But if A is strictly less than 0, then we consider the additive inverse of A, that is minus A. And since H is a subgroup, so minus A belongs to H, because A belongs to H. So its inverse is also in capital H. So in either case, so since H is a subgroup, so we can, so without loss of generality, we may consider A strictly greater than 0. Okay. Okay. Because in either case, you can find out one strictly greater than 0 integer inside capital H, right? Okay. So now define P. P is set of all H belongs to capital H, set of all A belongs to capital H which are strictly greater than 0, right? Suppose these are yeah, okay, suppose you may take this as x, yeah, x greater than 0. Now this set is non-empty as because A belongs to P, because A is a member of H which is strictly greater than 0. So P is a non-empty subset of, so P is a non-empty subset of the set of naturals N. So using well ordering principle, every non-empty subset of N must have a least element. So using well ordering principle, there exists N naught belongs to N such that N naught belongs to P is the least element of P. Okay. So you can find out one least element of P. Okay. Now our claim is that H will take the form N naught Z. Okay. Note that N naught being a member of P is in H, right? N naught being a member of P must be in H. And so any multiple of N naught must be in H, as because N naught Q is Q plus Q plus Q N naught times. Okay. Oh, sorry. Sorry. N naught plus N naught plus N naught Q times. Okay. Now H being a subgroup of Z plus and N naught belongs to H implies this will be in H. So this belongs to H. Okay. That means N naught Z is a subset of H. It is obvious that N naught Z must be in capital H. You need to consider the other inequality. That is, you need to show that H is a subset of N naught Z. So for the reverse inequality, let B belongs to H. Okay. Now our aim is to show that this B is a multiple of N naught. That means N naught will divide B. Okay. So here division algorithm comes in play. Okay. So by division algorithm, there exists Q, R belongs to Z, such that B equal to N naught Q plus R. Now what is R? R is the remainder sitting inside 0 less or equal to R less than N naught this. Okay. Okay. Now we show that this R is, this remainder will be 0. If not, if R not equal to 0, then then R will be written as B minus N naught Q, right? Now, if you look at this element, you will see that B belongs to H, okay? And also N naught Q belongs to H. So ultimately, using the criteria of a subset to be a subgroup, you can see that this R is actually in H, right? So this remainder is a member of H, and not only that, and this R is greater than 0. Since it is not equal to 0, so it is greater than 0, and it is strictly less than N naught. So having this property, you can say that, so we can see that this R is a member of the set P, and R is strictly less than N naught, which violates the least property of N naught in P, right? Because you found an element R sitting inside P which is strictly less than N naught. So how could it be possible to say that N naught is a least element? But we have assumed that this N naught is a least element. So whatever we have assumed for R was wrong, right? So this leads to a contradiction. And hence R must be 0, that is B okay. Yeah. So this violates the least property in P, and so this leads to a uh, contradiction. Okay, and hence R equal to 0, and so B will take the form of N naught Q. That means B belongs to N naught Z. Thus H equals with N naught Z. And this proves that every subgroup of Z plus is of the form NZ, n greater equal to 0. Okay. Okay. Fine. So in this way, we have characterized all the subgroups of the group Z plus. Okay. Okay. Now, if one asks a question that how could you find out the subgroups of the group NZ plus? Okay. Now the question is that what are the subgroups of NZ plus for any positive integer n? What are the subgroups of NZ plus? Okay. So what would be your move? So suppose that H be a subgroup of NZ. Okay. So being a so yeah. So being a subgroup of NZ and NZ is a subgroup of Z plus. So H will be a subgroup of Z plus actually, right? And being a subgroup of Z plus, so this turns out to be of the form n not Z, right? Since it is a H is a subgroup of Z plus, so H will be some NZ, right? For some n greater than equal to sorry n not greater equal to 0. Okay. Now okay. Now n naught is n not 1, right? So therefore it belongs to H. Since H is the n not 0. H is the subgroup n not 0. So n not is in H, right? But H is a subset of NZ. Being a subgroup of NZ, so H is a subset of NZ. That means this n naught is actually in NZ, and this implies that n naught must be of the form n q star, right? For some q star belongs to Z. Okay. So we have seen that n naught is a multiple of n. So this implies n naught is a multiple of n, right? So this proves that for a subgroup H of NZ, where if H can be written as n naught 0, then n divides n naught. So n is a, that is, n is a factor of n naught, right? So n is a factor of n naught. Okay, and conversely, any set n naught z where n divides n naught must be a subgroup of nz, as because if you consider two elements from n naught z, as because n naught q1, n naught q2, so it is actually n naught q1 minus q2, so it belongs to n naught z, and any element n naught q is actually, since n divides n naught, so n naught will be written as some n q dashed q, where n naught is n q dashed. So this implies for some q dash belongs to z. So n naught q becomes a multiple of n. So that means n naught q belongs to nz. That is, n naught z is a subset of nz where n divides n naught. Okay. So in this way, thus the subgroups of nz plus are precisely of the form n naught z, where n divides n naught. Okay, or you can say that n naught is a multiple of, or n naught is a integral multiple of n. Okay, okay. Now I would like to give you an exercise that characterize all the subgroups of Zn plus. Yeah, okay, for n greater than 0, n greater equal to 2. Okay, characterize all the subgroups of Zn plus. So this is your task. You need to check what are the subgroups of Zn plus. Okay. Okay. So now let us move to the discussion of uh, some more subgroups that can be generated by any non-empty subset of a group. We have seen earlier that if you take any element A in a group G, then that A, suppose you are considering one non-identity element A, and with respect to this element, you can construct a cyclic subgroup, right? So that means, so given any group and given any non-identity element of that group, you can construct a subgroup which is called cyclic subgroup of A, and which is the smallest subgroup in the group containing that element. Okay, so remark is that for a group G, suppose we are considering non-trivial groups. Okay, whenever we are talking about groups, we are considering non-trivial groups. We do not consider the trivial condition. Okay. Okay. So for a group G and for a non-identity element A belongs to G, the cyclic subgroup of G generated by small a, right? That is L angle R angle A is the smallest subgroup of G containing small a. Since if H is a subgroup of G such that A belongs to H, then any a to the power n belongs to H or all n belongs to Z. That is the cyclic subgroup L angle R angle A is a subset of H. And in view of this, you can say that this subgroup is the smallest subgroup in G containing A, right? Okay. Now this observation will lead us to the next discussion. Okay, that suppose instead of taking any element, we are considering a non-empty subset in that group. Then how to generate a smallest subgroup containing that non-empty subset of the group? Okay, so how to generate a smallest subgroup in the group G containing that non-empty subset, suppose A, small capital A. Okay, so that is the question. So how to generate? So what is the idea behind this construction? The idea lies upon the fact that this problem, that let G be a group, okay, then the trivial case will be intersection of two subgroups of G is again a subgroup. Okay, and the general situation is that also holds that for any collection of subgroups of G, the intersection of any collection of subgroups of a group G is again a subgroup of G, right? The intersection of any collection of subgroups of a group G is again a subgroup of G. Okay. Now I would like to prove the general case. I don't want to prove this one. Okay, I would like to prove this too, because the scheme of the proof will be same for the case 1 and case 2 both. Okay, and the actual situation deals with the property of intersection of sets. Okay, so let us have a look. So let H alpha be a collection of subgroups of G, collection of subgroups of G. Okay, okay, fine. Okay, then let H is the intersection of H alpha. Suppose alpha belongs to some index set delta. Yeah, delta be an arbitrary set. Okay, so H is the intersection of H alpha. Okay, now you need to check that this H is again a subgroup of G. Okay, now as you have seen that any subgroup of G contains the identity element of the group, right? Now the identity E belongs to H as it been in each H alpha. Okay, so the identity is in capital H. Now to check that whether H forms a subgroup, we need to consider. So let A B belongs to H. Then A comma B belongs to H alpha for all alpha belongs to delta, right? Since H is the intersection of H alphas, so A and B will be lying inside each H alphas, since it is the intersection, right? So AB belongs to H alpha and H alphas are subgroups of G. So this implies AB inverse will be in H alpha for all alpha belongs to delta, and being in every subgroup H alphas, so AB inverse is sitting inside the intersection H alpha, which is H, and this proves that H forms a subgroup of G. Okay, fine. I think it is okay. You do not need to worry about the proof because the proof is very simple. Okay. Now I would like to move on to the discussion of constructing the smallest subgroup of the group G containing a non-empty subset. Okay. So now let G be a group and capital A be a subset of G, which is taken to be non-empty, which is non-empty. Okay, because okay, yeah, okay. So let us first we do not need to write down first that it is non-empty. Okay, so let it be empty. No worry about that. Yeah. So suppose A be a subset of G. Okay. Yeah. Then you can show that the intersection of all subgroups of G containing A will again be a subgroup, as you have seen in the last result in the problem, that intersection of any collection of subgroups is again a subgroup. So intersection of any subgroups, intersection of all subgroups of G containing A will again be a subgroup. So then we denote it as L angle R angle A, that is the intersection of all subgroups of G containing capital A. Okay. Okay. Then this is defined to be the subgroup of G generated by capital A, being a as it is a, I'm not going to, okay, as it is a subgroup of G, right? So this is defined to be the subgroup of G generated by A. Okay. Now, if A be a singleton set small a, then this is the cyclic subgroup generated by small a, right? Okay. So let us have a look at some example that, okay. So first of all, note that being the intersection of all subgroups containing A, so it must be the smallest one, right? So note that this is the smallest subgroup of G containing capital A. Okay, so you need to remember with respect to which subset it is smallest. So this is smallest, this subgroup is the smallest subgroup of G containing that A. Okay, that you should remember every time. Also, suppose you consider A to be empty set phi, then what is the smallest subgroup of G containing A? A has nothing, A has no element. So what would be the smallest subgroup of G containing A? It is the singleton E. Okay, why? Because it is true vacuously. That means if it is not, then you need to find one element from an empty set which is non-identity, right? But you cannot find out any element because it is an empty set, right? So this shows that vacuously this will be the singleton set E. Now if you take the whole group, then the smallest subgroup will be the whole group itself for any group, right? Right? Now let us move to the previous case of cyclic subgroups. Suppose A is a singleton set containing small a. Then it is actually the cyclic subgroup generated by small a. It is a to the power n, n belongs to z. Okay, for all a belongs to G. For any a in G, if you take this singleton, then the smallest subgroup generated by this singleton will be the cyclic subgroup generated by small a. Okay. 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 Now, one case you might be interested in is that if the set A itself forms a subgroup, then so suppose A, so this is A, yeah, you can prove that the smallest subgroup generated by A will be A if and only if A itself is a subgroup of G. Okay. Now let us move to the discussion on the fact that the smallest subgroup, suppose you have a group and you are considering one subset A, then the smallest subgroup generated by capital A has elements which looks like something like that. Okay, so let us let us write down a statement that suppose let capital A be a non-empty subset of a group G. Okay, and this is the subgroup generated by capital A. Now we are looking for the we want to visualize the elements of this group. How do they look like? So that is our interest now, that how the elements of this group look like. Okay, now the situation is very easy. So then I just want to write down the elements. What are those? So these are actually like that. Yeah, A1, yeah, A2, AN. Okay, so these are the elements are the product of A1, A2, AN. Now what are these elements? These A1, A2, ANs. So these are, so in this product either AIs or its inverse is in A. Okay, and N belongs to Z plus or N. Okay, you may write it down as N. So this subgroup contains comprising of those elements which looks like these finite products of elements A1, A2, N, where these AIs or AIs inverse are in capital A. Okay. Okay. That means the elements will be like that, this type of. elements A1, A2, suppose it is AI, and after that AI1 plus 1 inverse, inverse, AN inverse. Just this is a particular case. I'm not giving you the whole story. Okay, I'm just taking one example of elements. Suppose A1, A2, AI plus 1 inverse, AI2, AI plus 2 inverse, AN inverse. Okay. Now these A1, A2, AI, these are in A, and AI plus 1 inverse. So the inverse of AI plus 1 inverse is in A, because these elements, these AIs are all in A. So in this product, either these elements are in A or the inverse of these elements are in A, right? AI plus 1 inverse and the inverse. So this is AI plus 1 and this is in A. Okay. So either the elements are in A or their inverses are in A. So that is the criteria. Okay. So the smallest subgroup generated by capital A, comprising of the elements which looks like a finite product A1, A2, An, where each element or its inverses are in the subset A. Okay. So how to prove this theorem? Please give me 1 minute. Okay. So yeah. So what is the idea of the proof? The proof begins with the definition of a set having this type of elements. Okay. So the proof, okay. So let capital H is comprising of a set having this type of elements, the finite products, where AI or its inverse is in A and N runs over the natural number set. Okay. 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 Now, so we want to show that this H is coincides with L angle R angle A, the smallest subgroup generated by A, right? So this is our aim, that this H will coincide with the L angle R angle A. Okay, that means you need to prove that first of all H contains capital A, right? Okay, okay. So yeah, so if yes, so if